Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Hello. This problem is similar to other mass spectrometer problems because we're considering a charged particle moving in a circular path in a uniform magnetic field. Now, what we need to first determine is what is the charge of this particle. So what we're going to do is look at the motion of the particle, compare it to the conventions of the right-hand rule for a positive charge, and see what that tells us about the actual charge of this particle. So what do we have in this problem? What is the situation? We have a region of space that has a uniform magnetic field, always heading completely out of the screen. I'm only going to draw a few of these vectors, but we usually represent them as a dot and a circle or something like that heading out of the screen. We also have a charged particle moving in a circular path, say maybe starting around here and heading around 1/4 of the circle like this. And of course, it would continue its circular path. We're only drawing 1/4 of it. So we have a charge Q here. Now, let's consider the motion of this charge to help answer part A, meaning whether or not this charge is positive or negatively charged. So let's look at this charge's motion. We see that it has, at the beginning, let's pick a particular point in its motion. Let's talk about the beginning. In the beginning, its velocity is directly upward. And because its circular motion is heading like this, we know that the acceleration, because of uniform circular motion, is always heading into the circle. So it's going to be heading directly to the left. Now, because it's accelerating to the left, that means the net force is also to the left, but the only source of any force is the magnetic field. So the total force is headed to the left, and therefore the magnetic force is headed to the left. Now, we know all the vectors that make up the right-hand rule for the magnetic force. So we can apply the right-hand rule here, see if it agrees with a positive charge convention, and if it does, then this charge is positive, and if it doesn't, this charge is negative. So let's apply the right-hand rule here. What do we do with our right-hand rule? Well, we put our pointer finger along the direction of the velocity. In this case, it is directed upward. So it's going to be like this. Then we have to take our middle finger to represent the direction of the magnetic field and point it out of the screen. So when we do that, we have our pointer finger going up like this. Now when we do this, we have to kind of twist our wrist, and that means that our thumb is actually, let me write the magnetic field on the other side here. Our thumb is actually pointing this way, and that's going to be then the direction of the magnetic force given our convention of the right-hand rule for a positive charge. So we see here that the motion of this particle doesn't actually agree with the convention of the right-hand rule for a positive charge, and therefore this charge must actually be negative. So this is actually a negatively charged particle, and that is because when we do our right-hand rule out, assuming it's a positive charge, we observe the opposite type of motion, and therefore we must infer that it is actually a negative charge instead. Now, the next part of this question is asking for the mass of this particle, and it gives us all the other information we need to relate the qualities of this particle and the magnetic field to the circular motion. So remember that the radius of a circular path is given by the mass of a particle multiplied by its speed, divided by the charge of that particle and the magnitude of the magnetic field through which the particle is traveling. If we want to find the mass of the particle, we can then just solve for it here. So let's do that. If we do that, we have that the mass is equal to the charge of the particle multiplied by the magnetic field to which it's traveling, multiplied by the radius of its circular path, divided by the speed with which it is traveling. So when we plug all these things in, the charge of our particle is given to be 8.2 times 10 to the negative 4 coulombs. The magnetic field through which this particle is traveling is 0.48 teslas. The radius through which it's traveling is quite large, 960 meters, and we're going to divide that by its speed, which is given to be 140 meters per second. Put this in our calculator, do everything out correctly, and we'll see that the mass of this particle is a little small, It is 2.7 times 10 to the negative 3 kilograms. Here, let me rewrite that 3 a little better. And there you go.